This video deals with calculating the derivative of a function using first principles. A function f is said to be derivable at x equal to c if limit is h tending to 0 to the right, f of c plus h minus f of c by h, that is the right hand derivative, equal to limit as h tending to 0 to the left, f of c plus h minus f of c by h, that is the left hand derivative. So f is said to be derivable at c if the right hand derivative equal to the left hand derivative, or if limit is h tending to 0, f of c plus h minus f of c exists by h exists, and we denote it by f dash c. Question 1. Discuss the differentiability of fx equal to mod x minus 5 at x equal to 5. The right hand derivative is limit as h tending to 0 to the right, f of 5 plus h minus f of 5 by h, that is limit as h tending to 0 to the right, mod of 5 plus h minus 5 minus mod of f of 5 becomes mod of 5 minus 5 by h. That is limit as h tending to 0 to the right, mod h minus 0 mod 0 is 0 by h, which is limit as h tending to 0, h by h which is 1. The left hand derivative is limit as h tending to 0 to the left, f of 5 plus h minus f of 5 by h, that is limit as h tending to 0 to the left, mod of 5 plus h minus 5 minus mod of 5 minus 5 by h, which is limit as h tending to 0 to the left, mod h by h. When h tends to 0 to the left, h is negative, so mod h is minus h. So it is limit as h tending to 0 minus h by h, which is minus 1. So the right hand derivative is 1 and the left hand derivative is minus 1. So f is not differentiable at x equal to 5. Coming to question 2, examine the function f defined by fx equal to x bracket x, where 0 less than or equal to x less than 2 equal to x minus 1 into x, when 2 less than or equal to x less than 3 for differentiability at x equal to 2. Bracket x denotes the greatest integer less than or equal to x. Left hand derivative is limit as h tending to 0 to the left, f of 2 plus h minus f of 2 by h, that is limit as h tending to 0, h tending to 0 to the left, so h is negative, so 2 plus h will be less than 2. So f of 2 plus h will be 2 plus h bracket 2 plus h minus f of 2 would be 2 minus 1, that is 1 into 2 which is 2 by h. Now bracket 2 plus h, when h tends to 0 to the left, 2 plus h is less than 0, less than 2. So the greatest integer less than or equal to 2 plus h is 1. So this becomes limit as h tending to 0, 2 plus h minus 2 by h, which is limit as h tending to 0, h by h which is 1. The right hand derivative is limit as h tending to 0 to the right, f of 2 plus h minus f of 2 by h. H tends to 0 to the right, so 2 plus h is greater than 2, so we will take the value of fx as x minus 1 into x. So f of 2 plus h will be 2 plus h minus 1 into 2 plus h minus 2. That would be limit as h tending to 0, 1 plus h into 2 plus h minus 2 by h, which is limit as h tending to 0. When you open the bracket, you get 2 plus 3h plus h squared minus 2 by h. That is limit as h tending to 0, h into h plus 3 by h. So the h cancels and you get limit as h tending to 0 of h plus 3, which is 3. So the right hand derivative is 3 and the left hand derivative is 1. So the function is not differentiable at x equal to 2. Question 3. Fx equal to x squared when x less than or equal to 1 by x when x greater than 1. Discuss the differentiability of f at x equal to 1. The right hand derivative is limit as h tending to 0 to the right, f of 1 plus h minus f of 1 by h. That is h tending to 0 to the right, so 1 plus h is greater than 1, so fx would be 1 by x. So f of 1 plus h would be 1 by 1 plus h. F of 1 is 1 squared, which is 1 by h. Taking the LCM, this limit as h tending to 0, 1 minus bracket 1 plus h by h into 1 plus h, that is limit as h tending to 0 minus h by 1 plus h. The h cancels and substituting limits you get minus 1. Left-hand derivative is limit as h tending to 0 to the left, f of 1 plus h minus f of 1 by h. H tends to 0 to the left means h is less than 0, so 1 plus h is less than 1, so fx would be x squared. So f of 1 plus h would be 1 plus h the whole squared minus 1 by h, that is limit as h tending to 0, 1 plus 2h plus h squared minus 1 by h. The 1 cancels, you get limit as h tending to 0, h plus 2. Since taking the h out from the numerator, the h cancels. Substituting the limits, you get 2. So the right-hand derivative is minus 1, left-hand derivative is 2, so f is not differentiable at x equal to 1. Find the right-hand and left-hand derivatives at x equal to 1. Hence, find the condition for the existence of the derivative at x equal to 1. Fx equal to ax squared plus 1 when x greater than or equal to 1 equal to x plus a when x less than 1. The right-hand derivative is limit as h tending to 0 to the right, f of 1 plus h minus f of 1 by h. H tends to 0 to the right, so h is greater than 0, so 1 plus h is greater than 1. So f of 1 plus h would be a into 1 plus h the whole squared plus 1. F of 1 would be a plus 1. So this is limit as h tending to 0, a into 1 plus 2h plus h squared plus 1. Opening the bracket, you get minus a minus 1 by h. That is limit as h tending to 0, a plus 2ah plus ah squared plus 1 minus a minus 1 by h. The a and 1 gets cancelled. The h cancels, so you get limit as h tending to 0, 2a plus ah, which is 2a. The left-hand derivative is limit as h tending to 0 to the left, f of 1 plus h minus f of 1 by h. H tends to 0 to the left means h is less than 0. So 1 plus h is less than 1. So f of 1 plus h would be 1 plus h plus a minus f of 1 is a plus 1. So f of 1 is a plus 1. So you get limit as h tending to 0, 1 plus h plus a minus 1. The a and 1 cancels, the h cancels and you get 1. Since f is derivable at x equal to 1, left-hand derivative equal to right-hand derivative. So one derivative is 2a, that is the right-hand derivative. Left-hand derivative is 1. So we get 2a equal to 1, so the value of a is half.